Hello everyone, welcome to the webinar. Today we have Sarah Dowling and Stuart Nicol, Senior Metallurgist at Glencore Technology. Sarah has over 10 years experience as a metallurgist across production, laboratory and process design roles. She holds a Master of Science in Chemical Engineering from the University of Cape Town and has worked on mining and metal refining projects all over the world, working with a range of base and precious metals in a variety of systems. Sarah now works within Glencore Technology's hydrometallurgy team as a senior metallurgist specializing in concept and feasibility studies for the Albion process and other Glencore Technology-owned technologies. Dr. Stuart Nicol is a senior metallurgist in pyrometallurgy team at Glencore Technology, specializing in ISACYCLE and related technologies. With over 10 years of experience in pyrometallurgy, Stuart has experience in both the design and operation of metallurgical plants across multiple commodities and processes. He earned his PhD at the University of Queensland in pyrometallurgy, focusing his research on phase equilibria and reaction kinetics applicable to industrial operations. Stuart's current role includes the development and study of basic and detailed engineering projects and site construction and commissioning for the ISASmelt, ISAConvert, PBOC, and other Glencore Technology-owned technologies. First, some housekeeping. You'll find you are muted. This is to keep things quiet for the webinar. Ignore the raise hand question and use the Q&A icon for any questions. Feel free to ask questions along the way. Once the presentation is over, we will still be on air taking your questions. Let's begin.
Oh, thanks for the introduction. So this particular webinar will explore some process development we've done for secondary copper. So at Glencore Technology, we often develop new flow sheets, new process, new chemistries for our clients due to changes in complex feeds and process challenges across the industry. So we did a lot of R&D on this the last few years, and this is the first time we're presenting this on a webinar, and we've got a few patents in this technology, which are provisional at the moment, but does protect a lot of the knowledge and know-how that we've developed in all the years and time we spent on the R&D in this. So this particular webinar is on secondary copper, which is very important as we're going towards a more renewables future with a high demand on renewable energy as well as electronics. So this will feature the ISACYCLE technology as well as our OxiLeach technology. So first up, a bit about Glencore Technology. So at GT, we're a technology solutions provider for the minerals and metals industries. So all of our technologies were developed in Mount Isa mines in Queensland, Australia, as well as a few other Glencore sites around the world. So we've been doing this for a very long time, and all of our technologies were developed for real plant problems. And so we've got a number of technologies in our suite. We have the ISAMill for ultrafine grinding. We have the Jamison cell for flotation. We've got the Albion process, which is used for oxidative leaching of metals and sulfides. We have the ISASmelt technology for smelting. And we also have the ISACYCLE team for refining. Now, within that technologies, we also have a range of additional products. In this particular webinar, we'll talk on one of the sub-products within the ISASmelt group, as well as another sub-product within the Albion process. So we're based here in Brisbane, Australia, but we have got offices all around the world. We've got well over 140 employees at the moment. We're currently expanding. And we've got a lot of installations globally, over 650, and that number grows each year. And we're doing a lot of innovation, so well over 40 years of continuous R&D and developments. So this particular talk will be about secondary copper. Now, secondary copper is from end-of-life consumer materials. So this is cables from houses, you've got things from cars, you've got electronics, radiators, other sorts of coppers. Now, not all secondary coppers are the same. So in your post-consumer materials, you have high-grade copper, which is very, very high purity. So you don't need to do much to it. You can basically melt it and make another product. But the challenge comes about when you've got medium and low-grade scrap as well as E-scrap. So these materials are more complex and challenging. They contain a range of minor metals and complexities and things there. And that's really the challenge, is how do we take that copper-rich material and extract the copper as well as remove all the impurities. And that's where a lot of the knowledge and know-how and challenge is in the secondary copper industry. So the idea is we take these post-consumer materials, we treat them, we produce new metals, and we put them back into the circular economy for just a better overall sustainability. So you have lower emissions and overall ESG improvements with secondary materials as opposed to primary ones. So when we look at those low-grade materials with high amounts of impurities, generally we've got a very, very complex flow sheet. So most low-grade secondary copper plants use what's considered the Knudsen flow sheet. So this one consists of oxidation and reduction and then refining. So a number of steps and processes. So we've got all these steps and processes to extract the different metals and produce that final copper product. So some metals are more easily oxidized, some are more easily reduced, and there's also some special chemical process as well along the way to pull them out and pull out the impurities. The flow sheet is more about impurity removal rather than copper production. So there's 3 stages of the process in the Knudsen flow sheet. The first stage is reductive smelting or primary smelting. In the primary smelting step, we take the secondary copper materials and we smelt them under highly reducing conditions. So this produces a clean slag as well as what we call a black copper. So that black copper contains 80%, a bit higher, a bit lower at times, copper, as well as a whole range of other base metals. So that includes things like lead, tin, zinc, nickel, as well as all the precious metals. We can't send that black copper directly to the tank house because it contains tin, as well as other metals like lead and nickel. So we have to convert that to remove those other base metals before we put it to the tank house. So we do that in the converting stage. So in the converting stage, we can do either oxidation to produce a tin slag, or we can do fuming to produce a tin fume. So each has advantages and disadvantages. Tin slag is the more common process currently used, but tin fuming has been used historically. There are some advantages and disadvantages to both. After converting, you produce what's called a raw copper product. So this is high copper and very low on the other base metals after you go through the converting stage. That raw copper you then put through an anode furnace, which does further impurity removal, as well as reduction to remove the oxygen from the copper. It's cast into anodes, then sent to the tank house, where it gets refined to produce copper cathode, as well as precious metals, and sometimes nickel sulfate. So you can see that this flow sheet is quite complex. Lots of steps, lots of processes, lots of things going on. And this is a challenge. So in secondary copper, there are 3 major challenges with the Knudsen flow sheet. The first one is economies of scale. Because the flow sheet is so complex and there's lots of equipment, that means you have to have a lot of things to make the plant work. And that makes the barrier to entry quite high, and most of these plants are quite large in scale to get the economies of scale to make the sites profitable and things there. So it means that people have to go for very large facilities. The other one, of course, is the work in progress, or what's called WIP. So that means because you have all these steps, the material sits in your flow sheet for quite a long time, particularly because we're using electro-refining, and the tank house it sits in there for a number of days depending on the operation and things there. So some tank houses can have like 22 days of copper just sitting there. Because all the secondary copper contains a lot of precious metal, there's a lot of metal inventory or working capital locked up in these plants. So you can see if you're processing e-scrap, you can see roughly, if you're processing about 20 KTPA of e-scrap, you've got $30 million of metals just locked up in your work in process, which is a huge capital cost, which is often hidden. The other one, of course, is partial metal recovery. So some of the flow sheets try and overcome challenges 1 and 2 and go with simpler flow sheets. So some people try and take e-scrap and smelt it, or and just recover 1 metal or 2 metals. Other people try to do hydrometallurgy and they use aqua regia to leach out just the gold and silver. But they're leaving all these other byproducts behind, and that's a loss of potential revenue. So they're losing zinc value, they're losing tin value, they're losing lead value. So there's 3 major challenges with the flow sheet, and it all comes down to the complex flow sheet, the number of steps, and how long it sits in the tank house. So what you can see here is the conventional flow sheet that's used and accepted across the entire secondary copper industry for low-grade materials. So you can see that there's the 3 stages of processing. The first upfront reductive smelting stage, you have the converting stage, you have the fire refining casting as well as the tank house, and has all these challenges. So you can see in green where some of our technologies can be applied. We identified some of these problems and we decided to reassess and reevaluate and spend a lot of time and thinking and brainstorming ways to overcome these challenges and come up with a new process to overcome all these problems. So we came up with a new process. So rather than having converting, fire refining, casting, and electro-refining, we decided to go with our OxiLeach technology. So what this means is we do the first stage of smelting under reductive conditions, produce a black copper. We then put that through the OxiLeach technology, which leaches the copper into solution and produces a precious metal containing product that also contains your tin and your lead and other metals, and you can then directly electrowin the copper from solution. So what this does is it cuts out all those additional stages, all that additional equipment, reducing the capital cost as well as the time that the metal sits within the plant. So this also reduces the metal inventory cost, that sunk capital in that metal that just sits in the plant. So it brings down the capital costs and also improves other things. So Sarah will talk more about the OxiLeach technology and how that works, and I'll now talk more about the upfront stage of smelting, where we smelt to produce the black copper. But this particular flow sheet is very new, and we've got a provisional patent on the OxiLeach stage of the black copper. So if we look at the first stage of the flow sheet, is what we call reductive smelting. So in reductive smelting, we take the secondary copper, smelt it under reducing conditions. So there are three technologies which have been used in the secondary copper industry. For the earliest flow sheets, all used blast furnace technology, which used a lot of coke and other materials, and they also had challenges with fuming zinc from the plants. So a lot of the blast furnaces had high zinc slags and also had high operating costs because they used a lot of coke there. The next technology that was used was the top-blown rotary converter, or Caldo furnaces. These technologies were very good when they were invented and still employed across the secondary copper industry. The most recent and most modern technology we have is the ISACYCLE technology. So if you look, you can see a comparison between the ISACYCLE as well as the TBRC. So the ISACYCLE technology generally has longer campaigns than the TBRC, so less maintenance, less costs with maintaining the equipment. So generally the campaigns are about 4 times longer for the secondary copper industry. We also have higher lance efficiencies, so well over 99%. So this improves the processes and the off-gas systems and other processes there. We also ramp up very quickly. We've got very good fugitive emissions controls, and we can do a lot of chemistry advantages, which I'll detail more coming up. So you can see one of the more important things is the ramp-up time for these technologies. So our technologies we can ramp up very quickly. All of our ISASmelt and ISACYCLE technologies have been ramped up to nameplate capacity in less than 12 months. While TBRCs, other furnaces, other technologies typically take longer to ramp up. So the question is why is this ramp up so important? So the ramp up is effective capital costs to your plant. If you're not at nameplate, you're not fully utilizing the asset, and that's lost revenue. So you can see if you're during the ramp up stage, you have low metal production, high labor costs, high maintenance costs, and you'll also be spending lots of money on equipment modifications and changes. So this is often not taken into account for plant capital costs, but has a huge impact on the overall project viability. So it's very important that when you do a capital assessment of projects to include the effective capital costs associated with your ramp up time. And you can see that's one of the advantages for what we offer. So if we look at the ISASmelt and ISACYCLE technologies, they're very similar. So they use the exact same furnace design, but some slight modifications. And so I'll now explain a bit about the technology and outline some of the key differences with the standard ISASmelt furnace. So like the ISASmelt furnace, the ISACYCLE technology has a steel shell with a refractory brick lining. So it's a simple system. We don't use intensive copper cooling elements. So this reduces the capital costs, increases the safety, and makes the plant and processes easier to run. With the advanced lining designs, we can get long campaigns without the need for expensive copper cooling components like bath blocks and waffle coolers and those sorts of things. So the furnace is fed through either the final feed device, which the feed can continuously fall into the bath where it gets smelted. We can also do pneumatic injection of high value materials. So E-scrap and high precious metal content materials can be injected pneumatically down the lance where it gets injected directly into the bath. So this pneumatic injection of these high value materials is a key differentiator with our standard ISASmelt designs. So the feed material gets poured down the final feed device or injected down the lance where it reacts in the bath. So the process is driven by oxygen, which is blown down the lance into the slag bath. So this drives the chemical reaction. So the lance pushes air into the bath, the oxygen dissolves into the slag, and the slag acts as the oxygen carrier. The slag carries the oxygen to the materials where it reacts to produce the molten products. The lance itself is a simple steel pipe. So it gets submerged in the bath, and the splash and the gases flowing down the lance cool the steel, and we can freeze a freeze lining on the lance itself. So this can protect it for a long time, and you can last for many, many, many days in the bath without having to change it out or swap it out with the advanced lance designs. The off-gas from the furnace is extracted through a off-gas port in the roof and then sent through conventional gas cooling cleaning systems. When we look at the ISACYCLE technology, because it's applied to secondary copper containing plastics and other materials, there's some differences in the off-gas handling and treatment systems. So things like halogens, dioxins and furans and NOx control, a lot of the systems there are a bit different. Of course, the molten products are tapped from the bath. So if we look at the ISACYCLE technology, we generally have two tap holes, a slag tap hole and a metal tap hole, because the density difference between the copper and the slag is sufficient enough that we have initial phase separation within the furnace. We've got very simple, robust tapping designs, which are easy to operate, easy to run, which is one of the key advantages for our technologies and a lot of the designs and operability of the plant there. We also have advanced control systems. So we've got advanced automation. You can see a control room operator there running the plant quite happily. So that's the basics of our technology and how it works. There's a lot of IP and know-how to make the technology successful and run on the industrial scale. So we often get asked how big our furnaces are. So we can supply any furnace of any size, all the way from a couple of kilos an hour up to millions of tons a year. So there's no limit to what we can design. So please, if you have a size or something like that, reach out. We have got standard design, but we also have designs which we can adapt for every project. And so we can go from the very small secondary copper plants all the way to the very big plants. So when we look at secondary copper specifically, that first stage is a reductive smelting. The reductive smelting stage is very important. The most important things for us is base metal chemistry control. So there are three elements which we need to focus on in the first stage of smelting. That's tin, lead, and zinc. So the most important one is zinc fuming. So we need to remove all of the zinc into the fume as much as possible. The reason being is zinc is effectively distributed in both the slag and the black copper under the conditions in the furnace. So we have to fume as much as we can. So the intense bath agitation of the ISACYCLE technology ensures that our technology has the highest rates of zinc fuming in the secondary copper industry. So you can see when you compare that to the TBRC and the blast furnace, we have close to double the rates of fuming. So this means we can extract twice as much zinc into the dust as other technologies, which generates additional revenue, and it also means that the slags have lower zinc levels. Some plants who use TBRCs and blast furnaces have to do downstream slag fuming. They have to invest additional capital to clean up and remove that zinc from that slag because they can't remove it effectively in the blast furnace or the TBRC. The other important one is lead, so that one also gets fumed off into the dust, as well as tin, and that gets pushed into the copper phase. So you can tell that what's very important for us is the high fuming rate, specifically the zinc, as well as slag chemistry control to allow that to happen. So when we talk about the slag chemistry control, this is very important for secondary copper operations. So there are two elements which are of concern to these operations. The first one is aluminium and the other one is zinc. So specifically the aluminium in the feed stabilizes what we call the spinel phase. So this increases the liquidus temperature or the minimum temperature you can have a fluid slag. And so we have to flux very carefully to ensure we have a fluid slag to keep the furnace operable. So aluminium is the most important one which we focus on. And so we have to flux that effectively. The other one, of course, is zinc. So zinc also impacts the operating temperature and conditions in the furnace, but we overcome this with the higher rates of fuming. So by having such a high fuming rate, we can run the furnace at lower temperatures at easier conditions. So that key element we talk about is aluminium. So generally sites flux this with a range of fluxes like iron, silica, lime, and other components depending on the chemistry and the processes they run. A lot of furnaces, when they run with batch operations like TBRCs or blast furnaces, due to the limited ability to measure and control the slags, a lot of these plants, based on literature information, appear to be slightly overfluxed in these systems. So that means they operate above the liquidus temperature, so they got very hot, very fluid slags, which are corrosive to the refractory. By comparison, we run below the liquidus temperature with some solids in the bath. So this means we have a lower slag mass, we run with a lower temperature, and we also use less fluxes. So this means by having that intense bath agitation and good chemistry control, we can have high copper recovery, lower operating costs, and longer furnace campaigns, which improve the overall plant economics. So the other important question is that reductive stage of smelting. How reducing do we run it? So that key stage of smelting is we want to pull all those base metals, that's the lead, the zinc, the tin, the antimony, the gold, the silver, the nickel. We want to pull all that all into the copper phase. So we want to run that as reducing as possible as this pushes those elements into the copper and out of the slag phase. But there are some limits. So generally we want to run as close to ion saturation as possible, and that's one of our limits here. So we're going to run it as close and as hard to that ion saturation limit as possible for good chemistry and good control. So the reason being is there's two phases which we can form if we don't control the metal chemistry properly in secondary copper. So that liquid copper phase can also split out into multiple phases in that bath, which causes challenges. So the first challenge you have is iron, and the second challenge is sulfur. So that first challenge is iron. So if we run our furnace 2 reducing, we can start to form solid iron crystals in the bath. So those iron crystals will form masses in the copper, and it'll be hard to tap, it can bog up the furnace, and it'll be hard to run. So we want to run it in the fully molten region, close to, but not at ion saturation. And we want enough wiggle room so we don't form those solids. The other challenge has got to do with sulfur. So if you have got sulfur in the feed, you can form an additional phase, which is a matte phase. That matte phase generally gets trapped in the slag and represents a loss of copper as well as other metals to the slag. So we don't want to have that matte forming. Instead, we want to blend the feed, control the chemistry, so that we only have a small amount of sulfur in the chemistry, and so we have a fully one-phase copper metal phase, and we don't form that matte. So I hope my presentation gave you a brief outline of the ISACYCLE technology, how it works, and some of the chemistry challenges in secondary copper, and how we overcome that effectively with our technology with good process chemistry and design. So I'll now hand over to Sarah, who will outline that second step of our flowsheet, the OxiLeach process.
Thank you, Stuart. I will now take you through the hydromet part of this talk. Glencore Technology developed the Albion process for low-cost leaching of sulfide minerals. The Albion process consists of an ISACYCLE, the OxiLeach reactors, and the hypersparges. The Albion process is a simple, robust, and easy to ramp up process. The graph on the right shows that the Albion process featured a McNulty's Series 1 profile after 2 years of operation at GPM. This slide shows our now global footprint of the Albion process. We also have planned installations or projects in advanced design phase in the USA, the CIS, and the EU. Of note for this presentation is the installation at MacArthur River, where OxiLeach reactors were installed to leach copper mud from other Glencore sites to produce copper sulfate. Copper mud is 80% metallic copper. The copper sulfate product is used as a reagent in the lead zinc concentrator. The site saved millions of dollars as it no longer needed to purchase copper sulfate reagent. I will now touch on the reactor designs for black copper leaching. Leaching of high purity copper wire or granules for copper foil production is typically conducted in packed bed reactors. However, black copper is only 60 to 90% copper and contains precious metals and base metals. The stirred tank reactor allows for a low precious metal inventory and high oxygen mass transfer rates, whereas the packed bed reactor has a high precious metal inventory and it's very difficult to achieve high oxygen mass transfer rates. GT thus focused on atomization, followed by leaching in the OxiLeach reactor. Let's talk a bit more about atomization. In some way, this takes the place of the ISACYCLE in the Albion process, as it is the enabler for using simple stirred tank reactor technology, which is the OxiLeach reactor. The molten metal is fed to the atomizer where high pressure water jets break up and cool the liquid metal to fine particles. Water atomization is the correct fit for this process, as there's no need for spherical particles, and if some oxidation of the black copper occurs, there is no issue with that. Also, water atomizers can handle high throughputs. In the table, we have test results of atomizing black copper to 2 different particle sizes. The larger particle size requires lower water pressure, and this has a knock-on effect of requiring smaller pumps and smaller filters. However, the smaller particle size allows for very rapid leach at lower acidity, which opens the door to the direct electrowinning flow sheet. With a particle size of less than 75 microns, there is 16% of the material less than 16 microns, so ultra-fine. And this ultra-fine tail needs to be considered in designing the filtration system. This is not seen as a fatal flaw, however, and a P80 of less than 75 microns is the preferred sizing. Let's take a look at the design features of the OxiLeach reactors and how they are suited to black copper leaching. The OxiLeach reactors feature a down-pumping, high-solidity lower impeller for increased gas holdup. The hypersparge and the large hydraulic head promote rapid oxygen mass transfer. The OxiLeach reactor has a vented roof where processed gases can be vented to the atmosphere or captured in a scrubber. The shell is stainless steel and various grades are available, and GT offers welded and bolted tank designs. Bolted tanks are quicker to install, require no on-site welding, and can be installed by a low-skilled workforce. Recently, 400-meter cube bolted OxiLeach reactors were installed at MacArthur River, and the average time of on-site installation was 2 weeks per tank. Let's take a look at the black copper leach chemistry. As with the Albion process and leaching sulfides, we will soon see that it's all about the oxygen mass transfer. The graph on the left shows the increasing rate of copper leaching with increasing oxygen partial pressure. The experimenters reworked this data into this neat plot to show the dependence of reaction rate on oxygen partial pressure. On the right, we have a schematic of the reaction chemistry. Overall, the reaction chemistry is quite simple. Metallic copper and acid and oxygen react to form cupric ions and water. However, this schematic shows nicely the role of the cuprous ions. The equilibrium between metallic copper, cuprous ions, and cupric ions forms at the particle surface, and is why higher surface area or smaller particles allows for higher reaction rates. What is missing in this schematic, though, is the oxygen mass transfer from gas to liquid. If the particle surface area is large enough, the oxygen transfer rate becomes the rate-limiting step. Hence, all the features of the OxiLeach reactor which serve to increase oxygen transfer rate are advantageous to black copper leaching. Now let's look at some black copper leach results. For a P80 of less than 75 microns, a copper extraction of 98% was achieved in only 2 hours. The initial acidity was 90 gram per litre sulfuric acid, and the terminal acidity was 12 gram per litres. This low terminal acidity is required for the direct electrowinning flow sheet. For a P80 of less than 150 microns, the copper extraction was only 57% at 6 hours. The test was repeated at higher acidity, and a copper extraction of 99% was achieved in 4 hours. However, the terminal acidity was 110 gram per litre sulfuric acid, which is too high for the direct electrowinning flow sheet. The granulated copper sample with a P80 of less than 1,700 micron achieved a copper extraction of 99% at 20 hours. The initial acidity was 90 gram per litre sulfuric acid, and the terminal acidity was 19. This particle size distribution is most suited to a packed bed reactor, though, and we prefer to focus on the atomized samples, which were more suited to the OxiLeach reactor technology, which allowed for very low precious metal inventory in the reactor. I have made comment on the first 4 points on the previous slide. To continue, zinc, iron, and nickel are all extracted more than 90%, and antimony is extracted less than 20%. Lead and tin are extracted, but precipitate due to their low solubility. The precious metals are not extracted, and they report to the lead-tin residue. The high-level objectives of a black copper leach flow sheet are to recover precious metals and lead and tin to the leach residue, to recover the minor base metals such as nickel and zinc to hydroxide products, to recover the chosen alkali in an effluent treatment plant. In the black copper leach flow sheet, the bleed stream is determined by the largest soluble minor metal. So as an example, a black copper of only 83% copper but with a wide spread of minor elements will have a smaller bleed stream than a black copper of 90% with a single high impurity. the bleed stream ultimately determines the ratio of final ETP residue to feed and is an important consideration in the overall flowsheet design. To minimize final ETP residue, technologies such as acid recovery should be considered. This will result in a higher upfront capital expenditure, but will save on neutralization costs. This is particularly crucial for sites with small footprints and no space to expand, as any ETP residue will ultimately need to be sent to a tailing storage facility. The use of magnesia or caustic in the nickel and zinc recovery as opposed to lime obviate the need for cycloning or screening the gypsum out of the metal hydroxide product, and also serve to decrease the final residue quantity. I'll now hand back to Stuart, who will run us through the overall flow sheet.
Thanks, Sarah. I found that really interesting. So, I guess some of the major advantages of the combined ISACYCLE OxiLeach flow sheet. The ISACYCLE technology can produce a low zinc slag in a single stage. You don't need to do any subsequent fuming to produce a low zinc discard slag. You can recover all of the zinc, or almost all of it, into a zinc-rich dust, which you can sell off to zinc plants or other processes to recover the zinc values from it. The OxiLeach technology can rapidly leach that black copper produced in the ISACYCLE, reducing the amount of WIP or metal inventory, reducing the working capital associated with the plant. We can separate the lead and tin cleanly into that leach residue, which also contains a precious metal. So very importantly, that lead tin residue has very low levels of copper, which is very different from that converter slag, which has high levels of copper. So this means that the re-smelting of that leach residue is really simple, and you can produce lead products, tin products, and precious metal products very easily. The precious metal products, once you do that initial stage of residue smelting, can be easily processed into a precious metal ingot, which can be sold. So you can get the metal up in the front, through the smelter, produce your PM ingot, like a doré bar, and sell it off really quickly. This also opens the option up to do things like toll smelting of packaged materials, so chain of custody of materials through the smelter, if it's designed effectively that way. The copper-containing recycles are not generated, so you don't have black copper going recycling around and around and around. So it simplifies the recycles in the flow sheet by not having the converting or the anode furnace steps. Copper is recovered as cathode in the ISACYCLE tank house, so it can produce that copper product which you can sell. Your nickel and zinc are recovered as a MHP, mixed hydroxide precipitate product, which can be sold to others to refine. You can also put processes and plants to produce final nickel sulfate and other products as well there, but that very much depends on the local economics and what you can do and what you can sell there. Again, as I mentioned, because of the quick flow sheet and what you can do, if you design the plant well and it's the right scale, you can do chain of custody. So toll treating of batches as opposed to purchasing materials on the market. This reduces the risks and improves the economics of the plants. And of course, you can separate the smelting and refining as completely decoupled by the OxiLeach process. So this simplifies the operation and improves the overall operability and uptime of the asset. So I hope that presentation was interesting and informative. We've got a few questions in the audience, and so now we'll go to the Q&A section. We'll go through some of the questions you've got. Oh, thanks, Sarah. That was really good. I don't often get to hear all the details of the work you do, so it's good to hear about it finally. So I got a few questions in the audience. So if you're there listening live, please feel free to put your questions in the box, and we'll get through as many as we can. So I guess we'll swap between questions for me and questions for you.
Yep.
So unfortunately, because I'm talking first, it'll be a question for you, Sarah. So we got a question here from the audience, a bit about the industrial precedents for the OxiLeach reactors leaching metals. So you did talk a fair bit about all the test work that was done to prove that it worked on the bench scale, but are there any operating sites that already do metallic copper leaching in industry that show that the technology actually works on the bigger scale and we don't need to do too much scale-up work there?
Yep, so that's a fair question. As we As we showed in our presentation, the Albion process is installed in many different locations across the world. So for black copper leaching or metallic copper leaching in OxiLeach reactors, we have an installation at MacArthur River Mine in Australia here. And these OxiLeach reactors are leaching a material called copper mud, which is a smelter residue from other Glencore smelters. And this copper mud contains 80% metallic copper. So it's a very useful reference point in terms of what we need for residence times, for particle size distributions and such like. So that's our leading example of where this technology is currently installed and operating very well, because the plant has made millions of dollars of avoided costs in that they don't have to actually purchase copper sulfate anymore. They're now making it on site. Okay, another hydro one. So I'll roll right on. Who else does black copper leaching, and why is the OxiLeach reactor suggested over others? So I think what they're talking about here, Stuart, is the reactor technology type. So elsewhere, especially in the copper foil industry, they use packed bed reactors. So in the copper foil industry, they are taking chopped copper wire, loading it into a packed bed reactor and recirculating a lixiviant through that. Obviously, if you've got a full reactor of copper wire, you've got a big inventory there. And that's the big difference between the packed bed reactor technology and our CSTR OxiLeach reactor technology. We don't have that big inventory. We obviously don't. We want to get our precious metals out quickly. So we've chosen the OxiLeach reactor technology. And yeah, I suppose the other thing to mention is that it's very hard to get good oxygen mass transfer in a packed bed reactor compared to an OxiLeach reactor. And we have the further advantage in the OxiLeach reactors in that they are designed to be used with our hypersparge technology, which is probably one of the best technologies out there in terms of getting good oxygen mass transfer into a stirred tank. Righto, this is one probably more for you, Stuart. It was mentioned that the maximum capacity of the ISACYCLE is 450 kiloton per annum of e-waste. What are the restrictions to increase this further?
Thanks. Now, this is quite a common question we get asked, is how big can we build smelters for and things there. It very much depends on the commodity, the process and the chemistry, what limits the throughput through the furnaces. So sometimes the furnaces are limited by the molten bath generation rates, so how often you need to tap out and extract the molten materials from the furnace to do downstream processing, because there are some constraints on some of the equipment there. And then there are ways that you can add more capacity. But a lot of the time for secondary copper, particularly e-waste, which is rich in organics, the real bottleneck there has got to do with the off-gas systems, because all the plastics combust and that generates lots of carbon dioxide, which needs to get treated and sent through the off-gas system. Now, because you generate so much gases, the off-gas systems can be quite large. So generally the first stage of gas cooling and post-combustion, as well as dedusting and then scrubbing, that's generally where a lot of the limitations are. So that 450 KT is probably around a single off-gas train, but would need to work quite closely with some off-gas experts to look at how we can expand the off-gas system beyond that. So if someone did want to do more than 450 KT, we can more than likely engineer the solution, but it just will take us a bit of time and effort to get there.
Yep.
So I can see here there's a bit of a two-part question for us, Sarah. Now, I often get asked this one a bit about is automobile catalyst. So people want to see if they can slide some AutoCat in with the e-scrap in the furnace. Now, I guess the process and the chemistry of putting automobile catalyst in with the furnace does actually complicate the slag chemistry. So a lot of the traditional way that they process automobile catalyst is using an iron-based collector, an electric furnace, and they melt it all together and they collect it all at the end. Now, if we did use the e-scrap flow sheet with the copper as the collector for the platinum group metals in the automobile catalyst, there are some limitations. So you can feed a little bit, but not too much. And all the PGMs will then go through the black copper and probably then go through the OxiLeach one. But I guess for yourself, Sarah, can you feed the automobile catalyst directly into the OxiLeach reactors to extract the PGMs, or would you need to do some different chemistries there?
I think you would need to be looking at different chemistries. The the reason for that. I mean, you could feed it in, but it would pass straight through to your leach residue, and you would need to do your smelting step as we've defined in this flow sheet to clean out the tin and the lead. So you could use it as a point of entry, so to say, but if it's clean enough, it's probably worth leaving it for that final step of our flow sheet where you are cleaning up the lead and the tin from the precious metals. It's it's pretty high value already, and that's probably the point at which you'd want to put it in. Yeah.
Interesting. I guess it would probably at the end, or if it ends up with a leach residue, you have to be re-smelting again in the lead tin furnaces to then collect it all out there eventually. So it's probably better off going up the upfront stage anyway.
Yeah.
So another question for you. Now, again, when we look at those precious metal, people try and look at trying to leach those PGMs and gold and silver directly into solution. So what are the advantages of this mixed smelting hydrometallurgical flow sheet compared to that hydrometallurgical route where they use things like nitric acid and aqua regia to just target the precious metals?
Yeah, I mean, good question. And we like even as a hydromet, we like the pyro step up front because it very quickly gathers all your valuables into that black copper product. And in the hydromet only flow sheets, you're essentially separating up everything up front in your big, call it an aqua regia leach or whatever lixiviant you might be choosing, and you've separated out everything right up front, and then you've got to go back and try and recover stuff. Whereas this is sort of a sequential upgrading of your valuables to a point where you can cleanly extract that precious metal content from the lead and the tin. So just to maybe run through it from the top to the bottom, you've got your E-scrap going into your pyrometallurgical step. You're producing a black copper product. In the first step of the hydromet side, you're leaching that black copper product. And your precious metals are reporting to the leach residue. So again, very low work in progress of precious metals on the hydrometallurgical side. So you're getting your precious metals out in that leach residue, and from there you can use another pyro step to cleanly separate out the precious metals from that lead and tin. And I think the other point to note is that all of those precious metals are deporting through this flow sheet together. So again, in the hydromet only flow sheet, you're gonna leach everything, and you might be trying to recover, say, your gold, but you could be losing your palladium or your silver whilst you're recovering the gold. Whereas in this flow sheet, all the precious metals are staying together, and they coming out at a single point in that leach residue, which you then take for further refining. Yeah.
I guess it always makes sense to sort of bring down the concentration and concentrate it up before you start to separate them, and that gives you always more recovery, because even the leach residue contains both lead and tin. You probably need to smelt those out and produce a lead, slag and other things, and do things like our BBOC to sort of bring up the concentration before you start to split is probably the nicer route there for recoveries.
Yep, so that's what we're trying to do.
So I guess we've only got time for one more question here. And this is probably a bit one for me. So the composition of the e-waste and other secondary copper materials is extremely variable. So how do we handle this variability? So this is one of those challenges in the e-scrap industry, because every single circuit board and thing is completely different. So if you look at other secondary industries like secondary lead, there's very little variability within the battery materials. So it's fairly homogeneous as far as things go. So they still do homogenization. The problem is e-scrap composition varies from the age of the circuit board, the particular electronic component comes from, as well as other contaminants in there. So it makes it extremely complex and things there. So generally, a lot of the time people start with shredding. So this is partly to sample and then determine the metal contents in that material. And then once they shred it, you can then start to mix it. And this is probably the important one, is to sort of homogenize that shredded material as much as possible. So when smelting, we probably recommend feeding a single batch of material in the furnace and having a fairly consistent composition, because this means that you can monitor the furnace as you smelt and then bring the furnace under control as you're going along. So this means that you can bring the chemistry and the furnace under control before you tap out that molten slag and that molten metal phase. So this is important to make sure that you have that nice clean slag. So get it right before you get rid of it. It's probably the key there. So we have got a number of sensors and systems on the furnace as well as the process. So there's things like acoustic sensors, vibration sensors, which tell you about how the furnace is performing. So you've got high level indicators, and they tell you if there is a major problem. But then if you got it under control, you then start to use more accurate measurement techniques. So sampling the bath, measuring the composition, and bring it under even tighter control to bring it to where you want it to be. And there is other indicators as well in the off-gas system as well there. But there's a range of sensors and systems to get the process and the chemistry right. And we do have to do a bit of training and to get people familiar with how it all works, because it's not a straightforward chemistry or process, but we do that. And with all that technology transfer and know-how transfer, we give those fast ramp-ups, which we described in the benefits there.
Yeah. Now, would your F600 furnace help with this? Do you do practice runs maybe on the F600 so you know how the big furnace is going to work?
So it does come down a bit to how the site wants to run and do things there. So some sites may actually use the F600 for that first upfront stage of assaying the e-scrap.
Okay.
So if you have got a large batch of materials, you don't know exactly what's in it, and you need to pay for the materials effectively. So if you don't have a flow sheet with a short residence time, it might be 30, 60, 90 days before it comes out the other end. So assaying the materials before it goes to the plant is quite important. So once you've got the materials collected, some people are looking at using the F600 furnace to smelt and measure the content of the gold and the silver and the other metals in the material before it goes to the plant to then do all their mass balance reconciliation effectively there. Now, as well, some people are also looking to using it for new materials, more complex materials. As we sort of mentioned, people are asking about automobile catalyst. So people can use that to look at how much autocat and new chemistries and new processes once the plant comes in. Now, that's also important because the e-scrap composition is also changing over time. So understanding a bit about the new chemistries and new processes on the year-to-year basis as things start to change over time, that'll also be of value there. It mightn't be used on the day-to-day, but there are a lot of applications which may assist sites. Now, you don't have to have one to run the facility, but it may assist you with your long-term planning depending on the level of complexity and the variability of the feed materials and the future visions and plans.
Cool. Good to know.
I think that's probably about all we've got time for. So we've got a few more questions which we haven't had the time to get through. So please just send us an email, reach out, and if you have asked a question and we haven't gotten to you, we'll get back to you as soon as we can. So thanks.
Yeah.
And we hope you enjoyed it, and hopefully we'll see you at the next webinar we hold.